In this video, we are going to talk about the Beer's law. When monochromatic electromagnetic radiation passes through a thin layer of sample of path length, let's say L1 centimeter, the power of the incident radiation is different from the power of the transmitted radiation. Indeed, this incident radiation will experience a decrease in its power. So the power of the transmitted radiation is less than the power of the incident radiation. The transmission in this case is equal to Pt over P0, and the absorbance is equal to negative log T. On the other hand, if this same radiation passes through a blank solution of path length L of the same thickness centimeter, here the power of the incident radiation is equal to the power of the transmitted radiation, hence Pt is equal to P0. So the absorbance in this case will be equal to 0, while here is not equal to 0. And what do we observe here is that the absorbance of the solution is proportional to the path length and to the solution concentration. Indeed, if we prepare three solutions of the same analyte but in different concentration, let's say C1, C2 and C3, and each time C3 greater than C2 and C2 greater than C1, and the measured absorbance for each concentration is A1, A2 and A3. If we plot A against C, here C1, C2 and C3, the result is a straight line. Hence, we can observe that there is a straight line or a linear relationship between A and C. And this linear relationship is expressed as the Beer's law, which is A equals to epsilon times L times C. So C is the concentration of the solution, L is the path length, and epsilon is the molar absorptivity of the analyte. So this Beer's law, in this Beer's law we have the epsilon which is constant and the path length which is constant, so the variation of A depends on the concentration. Of course, if we change the path length, the absorbance will change, but if we maintain the path length constant, so the absorbance will be proportional to the concentration. Let's do this example. If we place a solution in this compartment cell, this solution has a concentration of 4 times 10 to minus 4 amp. So the analyte that is contained in this solution, its concentration is 5 times 10 to minus 4 amp. And the path length of this sample cell is equal to 1 centimeter. The emitted radiation that passes through this sample has a wavelength of 490 nanometers. The transmitted radiation has an absorbance. Its measured absorbance was 0.338. So the question is, what is the molar absorptivity of the analyte contained in this solution? Here we write the Beer's law, which is A equals to epsilon times L times C. So the molar absorptivity of this analyte is equal to A over L times C. If L is in centimeter and C is the molar concentration, the A is unitless and is equal to 0.338 over 1 centimeter times 5 times 10 to minus 4 amp. The result is 676 cm to minus 1 amp to minus 1. Here is the molar absorptivity of this analyte in this solution. Now, for the same analyte and the same path length, we have a different absorbance. Let's say A equal to 228. So the question is, what is the concentration of this solution, of the sum analyte? Here, the Bill's law is also A equals to epsilon L C. So the concentration will be equal to A over epsilon times L. And because epsilon, or the molar absorptivity, is constant, so it does not change, the absorbance is 228, unitless, and the epsilon is 676 cm to minus 1 m to minus 1 times 1 centimeter. Here we have centimeter and centimeter to minus 1 cancel each other. Hence, the value here is 337 times 10 to the power of minus 4 m. Here is the concentration for a different absorbance of 0.228.